let's try it. Modify the equation. How do you find a modified equation? Well, you just insert the Taylor series directly and then see what happens. Here we're focusing on our center point I, so we have to insert the Taylor series for everybody else. We should be able to do this sort of in our head, shouldn't be that hard. Here you have the difference between two. We can write up one series here. I plus minus 1 equals phi I plus minus delta x phi derivative plus delta x squared half 1, 2 plus minus, and then 3 and 6 phi 1, 2, 3 plus, and finally the fourth delta x 4 over 24 phi 1, 2, 3, 4, and then higher order. So what do we get here? Inserting the series. Here, the difference between these two series, the center point falls. This term, he will survive. We have minus and minus, so he will become plus. So I will have here 1 over 2 delta x. So that means I take the central scheme first. So I keep the 2. And the difference, I had 2 times him. That is 2 times delta x phi derivative. This looks actually promising. See that the x is going to disappear and I get back what I should. Second order term, he will disappear. It's a minus between them. Third order term, he survives. So I will have 2 of him. Delta x 3 over 6 phi 1, 2, 3, and then even higher order terms. Equals. And then on the other side, I keep the delta x square, clear number, delta x square, insert. Now we have the sum of the series, minus 2 times the center point, hence if the center point disappears, first order terms disappears, it's a plus plus and it's a minus between them. The third term, this one, he is going to survive. That's the first one. And I will have 2 of him, so it should read 2 times delta x square half phi double. Again, this looks promising. Get back the double derivative. Third order term disappears, since it's plus plus. But the fourth term, he will be there. So it will be 2 times delta x 4 and over 24 phi 1, 2, 3, 4, and then higher order terms. So that's the modified equation. And from this one, we now can say, yes, this scheme is consistent. Let the deltas go to 0. You see you are left with our original partial differential equation, as we should. Also, you can tell the order of this scheme. Delta x squared. Here you will then be left with delta x to the power of 2, and the same goes with this other term here, also the second order. Yes, this scheme is second order accurate. And then we can't really get any more information out of it. What will now be the difference if I jump to the UDS? This was a CDS, and now UDS. It's a little narrow, but it shouldn't be too hard. The only difference is then the first term here. No plus 1 and no 2 here. So I will have 1 over a single delta x. And then the difference the center point minus the negative Taylor series. What will it be? The center point, he will fall. And the first one I will have is this one, the first order term. Is negative here in the negative series, but he has a minus already, hence I will have delta x phi derivative, which is okay. I get back here the first order derivative as I should. The next term is going to be this one. It is going then to be negative, minus, you will read something like delta x squared half phi double, and then even higher order terms. So that's the only difference, jumping from a CDS scheme to a UDS. It's still consistent. Let the deltas go to 0, we get back the original equation, so that's okay. But now the order has dropped. This is a first order scheme, as you all know. First order upwind differencing. So this doesn't look too good. Now, what will this actually mean when you look at the physics? Well, what do we have here on the other side? Well, we have something with a Clay number and so on. And now if you rewrite this one, the UDS scheme, you can now write it on the form the derivative here, just multiplying in, equals, and what do we have on the other side? Well, we have 1 over the Clay number, and here I will have the double derivative, and now I will have something else with the double derivative. I will have plus, and what will it be? It will be delta x half, delta x half phi double, and then higher order terms as well. So definitely, yes, we have added viscosity into this problem, and we have actually added a lot. So this is not nice at all. We have 1 over the Clay plus delta x half phi double. So how should we rewrite that one? Let us multiply with 1 over delta x here. So then you can write it like delta x outside. Then you will have 1 over the Clay number based on delta x plus 1/2 phi doubles. For the central scheme, the local cell Reynolds number had to be 2 or smaller. But for the upwind scheme, it could be anything. But here you see what happens. If he is 2, you have double the viscosity. So very bad idea, of course. So this 1/2 here is going to kill anything. Physics, real physics in this problem. So of course, no, you should never ever use this first order upwind scheme. It's stable, yes, but at a terrible price. So using a modified equation here, there you can see what is going on. Questions to this one?
So is it better to use CDS?
Absolutely. So the central scheme is much more accurate, and also I would say it's an advantage that he will blow up if you do something stupid. The upwind scheme, he's stable no matter what you do. So you can give him sort of an impossible task and he will still provide you with an answer. He doesn't explode. I think that's a bad thing. For an engineer or a Fluent or CFX salesperson, they like that the code actually gives you an answer. If it's 50 or 100% wrong, they don't care. So I don't like that one. I prefer that the code actually blows up. I think that's much better. So of course nowadays I don't think many use this first order of wind scheme. We'll have a look a little bit later, more advanced of wind schemes. It's not so bad as the first order, but the effect will still be there. You add viscosity into the problem just to smooth things down and get a stable solution. Other questions? Yep.
If you're able to quantify the viscosity, is
Yeah.
there some tricks, dirty tricks to like compensate for it?
Yeah. It can't really be done here. I mean, this is sort of unquestionable. This one shouldn't be here. I mean, the viscosity in front of the double derivative, or the Reynolds number, if you like, should be given. So you sort of have no option here. Of course, you could do the trick that you wanted one Reynolds number, and then you say, I want to use this operating scheme because I know it's stable. Okay? So then you have to call this one. That is your Reynolds number. Okay? And then calculate what should it be then. Here is actually possible, but remember this is a one-dimensional problem, so constant delta x's. If you start messing around here with a more unstructured mesh, 2D, 3D, you're in trouble. But yes, it should be possible then to make this coefficient here in front of the double derivative your Reynolds number, the one you are interested in. Then you have to insert into the code a totally different Reynolds number, strangely enough. That should be possible. Second, another argument was with the Berger equation we saw last time. There we had time as well. And then you had an additional term here, minus something with a delta t. And yes, then it should be possible to get everything here correct in front of the double derivative, more or less. Sadly, that was based on then the linear version, as we have here actually, since this velocity, small u inside this Peclet number, should be a variable multiplied with him. So it is actually a non-linear problem, which we have linearized to be able to do this. So in the real world, no, you can't really do this good. You can get approximations, so it will be closer to what you are interested in. Yes, people are fighting with that. But I'm not sure if they actually have succeeded that much. So. But have a look into it. So then you write an article and publish it, and then I will take the theory into the course. Other questions? Let us now jump to finite volume. So this will now be sort of just an introduction into finite volume with structured nice meshes. We will come back to this with the unstructured meshes later. But a little bit of finite volume you should all know. So I put out on the home page this finite volume number 1, which then is based on the theory by the book by Patankar from 82, I think it was. Very easy to read, fun book, so definitely if you fall asleep sometimes, it's on its nice. But don't buy it, it's very expensive. So you have the PDF of it, so you have a look into it if you're interested. According to Patankar, and actually this overview over the entire CFD world, I quite like. So different ways to do things. The first and most obvious, of course, Taylor series, which then now, as you know, leads to finite differences. Then it's possible to go into the heavy world of math, really heavy. We are talking Hilbert space, functionals, very hard indeed to deal with it. I don't think many of you have had that much math, so it's tough. But it's possible then to rewrite your original equation into a variational problem. So you have a functional, a corresponding functional to your original problem that's now is to be minimized. And that can be very hard to find. Normally, I would say solid mechanics, structural mechanics. They are here. And mathematicians, of course, they love this. But for an ordinary engineer, he doesn't understand anything of it. It's way too complex. Luckily for the engineers, you can get the exact same formulation by looking at it much more simple in terms of weighted residuals. So this is where I would say we find finite volume, but actually also finite element. And actually this is where it all began with solid mechanics. So you have an original differential equation, partial differential equation. L here is just an operator, a lot of different derivatives. And then we approximate a solution, and then we insert the solution into the equation, and then we get not zero, we get a residual. And of course we want this residual to be as small as possible. That's our aim. So it's sort of again a minimalization problem. Get the residual as small as possible. Now, the original equation reads equal to 0. So it should read equal to 0 here. Meaning you can multiply this original problem with whatever you want, since it's 0 on the other side. So what we do here, we multiply with a weight function, a w, and then we take also an integral. It can still be done. If you integrate 0, you still get 0, so that shouldn't change anything. And you integrate over a suitable volume, or a suitable element. And now, to make it easy, we say the volume we are integrated over, a control volume, we just say that our weight function, he will be 1 if you are inside. If you are outside, he is 0. So he's just a switch, inside, outside. And then we just take the volume integral of this residual and set it equal to 0. Then I will call this finite volume, actually. Finite element, then this weight function, which actually could be anything, can be quite advanced. Also, I would say the behavior inside your volume, that's also quite essential here. What kind of variation do you allow for your unknown inside your volume? If it's just a linear or constant, then I would say you are talking about finite volume. If it's more advanced, second order polynomial, cosines, exponential functions, whatever, then you are using finite element. But we don't have any clear rule here. So either way, finite volume, finite element, that's sort of based on the same, the control volume formulation. Okay. So as a simple example, here it's Poisson equation, double derivative equal to something. But now we are thinking in terms of integral codes. So using the same notation as Patanka and also fatigue then, the center point P and then east and west. And now I look at my volume, I'll just put a volume around my center point, hence I'm going to need values here on the cell faces. Small west, small east. So starting with the original equation, you just take a volume integral of it. And then when you have a derivative in front, of course, you only get the argument back here. But you're going to need it on the east and west border of your control volume. The source term, whatever that might be, well, there you have to make a volume integral out of it. So that depends what he is. If he's a constant, and he's not a problem. If he changes with the solution, then you have to pay some special attention to this source term here, of course. So now the question is, how do you deal with the quantities that you are seeking on the faces here? We only have values for our trial solution, you might say, on the nodal points, west, east, and the center. So how can we evaluate these terms on our faces, on the cell faces? So here are a couple of suggestions. The first one, you say, my unknown is constant inside my volume. Well, you can do that, but then you run into problems. What are the derivatives, a value, a reasonable value for the derivatives on the faces, on little west, little east? It's not defined. You can't really do this. So, of course, the obvious choice, choose a linear variation. Very easy, very simple. So that one would work. This one, not defined. And then you could play around with more advanced functions if you like. But then I would say you jump into the world of finite element. So finite volume, you stop here. Maximum linear variation. Just to have a definition what we mean with finite volume versus finite elements. And if you do this, linear variation, and you use a uniform mesh, of course you get the exact same discretization as you would have done with finite difference. So no change there. But the background is quite different. You have an integral formulation of the problem. And if you can recall the first lecture I gave in this course, I said, if you are going to use an integral code, don't start here. Don't start with the original differential equations on this form. Start with the integral form directly. Because here you demand that your unknown is a continuous function with an integral formulation. You can have sudden jumps in quantities, that's still allowed. So you cover more physics by using the integral formulation directly. So here, I shouldn't have done this. I should have written this equation up directly and started here. Okay, choosing this linear variation, then this should be rather trivial. And using now the Papankar notation for the algebraic equation as well. The center point P with coefficient AP equals the sum of all the neighbors, and now maybe even also a constant as well. Simple equation system can easily be solved. So no problem here. Expounding the problem. And now we are talking about the same equation that we had in the example by Vertiger, the advection diffusion equation, linearized, because now we have to assume this velocity is known. And here I've used the viscosity directly. So, okay, now we are talking fluid mechanics. But of course, you could use a gamma there if you like, to have it more generic. And now it's again the same problem when you do the integral, volume integral of this equation. You will have something like this. And then a lot of what it is has to be decided, has to be found on your cell faces. For the viscous terms here, linear assumption should be straightforward. Now the question is these two guys, what should we do here? And there you have, of course, the choice, choosing either a central scheme or an upwind scheme. Central means linear variation. Finding a value here, you take a linear variation between those 2 points. If you choose a first order upwind, then you have to know what's the sign for the transport velocity. If he is positive, then you choose the center value to be the representation of the value to the right. You go upwind to find him. Here first it's a linear, and as you have now seen, so it's actually exactly what we have done, but with the example of the Fenziger. So this now should be the recipe, and again this one could be solved with a direct method, no problem. But again here, just to make sort of get an idea for the demand for spatial resolution, you think in terms of now the max-mean method, this one unknown based on all the neighbors, and then we have to make an iterative algorithm out of it. Then we have to divide by this bracket on the other side. And can we apply the method? Well, you can do it in your head here. The sum of the coefficients, this one plus this one, well then you have 2 times of this viscous term, u half disappears, and we have 2 times the viscous term here, so yes, it will add up to 1. And then the demand, all coefficients positive, that means this one has to be positive, and you can do some rearranging here and see that, okay, this means the local Celadon Pickley number must be smaller than 2. And this is now the argument for from Patankar. Using this central scheme gives very crazy results, he claims. So he just did an example here, very stupid results, so he doesn't like it. You can see here, you have 200 and 100 gives the center point value of 50, which is clearly unfeasible. And if you just switch them, then you get 250, so obviously this is very, very unrealistic, of course. What he actually has done, without saying it loud, he uses a Celadon's number of 4. Of course this blows up, as it should. So I think he should be at least fair enough to say so in his book, but he doesn't. So yes, it blows up and it should blow up. You have a too big Celadon's number. Now Patankar continues with the remedy of first order upwind. So if the small u is positive, then yes, you just choose the upwind point to the left. If it goes negative, okay, then you choose the other one to the right. And the scheme you get now looks something like this. And again, yes, the sum of the coefficient is 1. You add these two together, you have 2 times the viscous term plus u, which is exactly what we are going to divide with anyway, so the sum is 1. And now the demand, all coefficients positive? Yes, they are, no matter what you do. So this one unconditionally stable. And he now says, with the same example, you at least get more realistic values, which is true. Yes, they are more realistic since the central scheme was highly unrealistic. But if you have a peek into the analytical solution, I would say it's a questionable how realistic they actually are. So they are pretty far off from what they should have been. So yes, It's stable, but dangerously diffusing the scheme. Now we can make that one a little bit. That was the world according to Patankai. Any questions to that one? No? Let's see here. Following Verziger, chapter 4, it's a very small chapter, he starts with the correct equation, in my opinion. He starts with the integral version. He doesn't first write up the differential and then integrate. He does it correctly. So here you have a steady state problem. You will have the advection terms and the diffusion terms and maybe even a source term. And now they have been written in the form as a surface integral. So that is our starting point. Different mesh systems. Of course, it's this question here. Is it a collocated mesh? Where do you have your unknown? And also, how will you handle meshes that is not with a constant delta x and delta y? So here you see the nodes. They are centered inside each single cell. Here they have been organized so that the faces lies in between the distance here. So you see this one, he's not in his center in his own volume. So he's a little bit here to the left. So that's just a matter of bookkeeping. As long as you know what you're doing, it both should work. But be aware when you start stretching the mesh. Yeah, I won't go through the details here. Notation should be the classic Patankai. So I wanted to show you the example here. First order upwind, starts with that one, which then is, as you now know, terrible, unstable. The linear CDS scheme, then we quickly run into problems with stability, but it should be more accurate. And then you have more advanced methods. Quick, that's a famous one. You use some additional points outside just the two that we have done so far to create one single derivative. So doing this, using a quadratic upwind interpolation scheme, you have to go even one additional neighbor upwind. So not just to the east, but also to the far east as well. So then this one will be better than the first order upwind. It's second order accurate, but it's still an upwind scheme, still involves additional viscosity into your problem. So quick, you use it with care. That's my advice. And typically what you will do in practice, if you have a problem, you start out with the first order upwind. It's so very stable, so you should rapidly then get a solution, which is wrong, but you get it. And then when you have gotten the solution, you switch on more advanced schemes, and then you continue the simulation. So that is, in that sense, these crude interpolation schemes, upwind schemes, are still valid to use. And you have, of course, also higher order schemes as well. But they can be tricky to use. I'll come back to that a little bit later also. boundary condition has to be involved somehow. Algebraic equation system must be solved, and here finally example. So this is our example to be solved, now using finite volume. So we have the advection diffusion equation, but now we go into a two-dimensional problem. So we do the following. We give the velocity file, the velocity field should be listed here somewhere. Where is it? Here. So we have the x velocity, it's just x, y velocity minus y. It's a classical example where you get the streamlines as hyperbolas. So the stream functions will be x times y equal a constant. So you know the velocity field before you begin. The velocities, they are given. Our question is the unknown phi, whatever that might be. So here you can think of it as concentration, for instance, of something. And then you look at only the first quadrant in space and say the inlet up here, where the flow goes down, has initially no phi whatsoever. The outlet here will now be the Neumann condition, derivative equal to 0. The bottom wall is just a symmetry line, so again, Neumann condition there. And then to the left, here, along this, actually a streamline, no velocity is crossing the y-axis. But we have a concentration here of phi that will change from 0 to 1. So the only way now that the unknown quantity phi can enter into our problem will be by diffusion through the y-axis. Not advection, no velocity there at all. So you will get some phi inside here, depending on your choice of viscosity. And then we play around with both UDS and CDS schemes. So here you have the code of the recipe written out in detail. And here is what we should get in the end. So we will have a concentration here, isolines for constant phis, now ranging from 0 to 1. So depending on your choice of gamma, that's the diffusion coefficient. Here it is, what was it, 1 over 100. Here it is 1 over 1000. So the bigger it is, the more diffusion you will get. The smaller it is, the more narrow or more sharp these gradients will be, the tougher numerics to solve that one correctly. So let's see if we have the code here. So it should be this one. So I just have a switch here. I can choose central scheme or upwind scheme. Setting the gamma and setting the number of points. So here it's possible to play around with this one as you like. I use here an SOR, so I play around with an omega and also maximum number of iterations. And for finding the solution, I just choose an epsilon. So here, setting the boundary conditions, and then solving the equation system. Just following the recipe directly. So now let's see what we get. We should start with gamma was 1000, then we can just see what happens. 1 remember, we don't have a time in the problem, so what you see is now the iterative solution to the problem. And he operates very, very slowly. Now you know with the SOR, successive over relaxation, we should use the optimum omega. Squash him. And here I had chosen an omega which was quite small. So let's try a bigger one and see if we can speed up the process a little bit. Ah, a little bit faster at least. Still slow. So let's give him a challenge. And 1.9, that should still work, I think. Yeah, goes a little faster. Should still be able to find the solution though. But still it takes a long, long time. Now this is a 400 by 400 problem, so it's fairly big. So I should just get a nice and a good picture of the same solution as Fensiger has in the book. So it should be possible to find it here, rather straightforward. Gamma 0.01 isn't that big, so no problem. Now let's make it a little bit more crude. 100. So now it should be fairly correct with 1.7 as an optimum. I'm finding the solution quite nice. No problem there. And this was now with the central scheme. And go here. Should be this image that we have here. Now let's try the other one, first order upwind. CDS is 1. So now let's see what happens. Can do it like this. I think I did it the wrong way here. This is the upwind, the central scheme. The other one was the upwind. But again, you can't really tell the difference between those two. They will be very, very similar indeed. Although the first order upwind, as we know, has more diffusion with it, has more viscosity, so he will push more into it. The one to the right, that's now a smaller viscosity, gamma 1/1000. And now choosing an upwind. We should still make a solution here. No, he crashed. Nice image though. Let's try with a smaller omega. Yeah, you get something like this. And fairly decent solution, but not perfect. But still, he does a fairly decent job here with this first order upwind scheme. Now jump to the central scheme, and you will really see the problem. He crashes sort of instantly. He has a lot of trouble finding the solution whatsoever here. So to find a solution, I had to soften him down a lot. Actually, I had to use this, when was it? The omega 0.3. If I can recall, successive over relaxation. Omega should be between 1 and 2. That was a good one, a good choice. Now I have a 0.3. Now this is not over relaxation anymore, it's under relaxation. So that's just to soften the iteration process down. Calculating the updated or the change in the unknown, and then I only use 30% of them. I think this should be stable, if I recall correctly. More or less. Yeah, easy one. Easy one. So you can get some noise with these codes, but if you are careful, then the noise, strangely enough, will be born up here, and then you see a lot of noise, but hopefully that will be flushed out of your area before he makes your solution totally blow up. And again here as a conclusion, when you look at the anode, you can sort of look at the transport of whatever should be diffused through the y-axis. You have the second order slope for the CDS scheme, for the upwind scheme. Well, for coarse meshes, it's rather strange behavior, but finally he will settle down to the first order accuracy slope. For the actual anode, the central differencing scheme operates quite nicely. The upwind scheme has a quite large anode, and you have to have a lot of cells to get the accuracy down, to get a good accuracy for the solution. So quite expensive actually, but stable. So that's the whole point. You can see here, for very big delta X's, you still get a solution with the first order upwind. But for the central scheme, you have to start with a quite small delta X to survive one at all. I will put out this code for you so you can play around with it yourself. Some of them were quite funny actually. So I have just listed some suggestions that I played around with to achieve a solution for n equal 100 and n equal 40. So I'll put them out on the homepage so you can have a look at it. Okay, then we are missing a little bit, but I will address that one tomorrow. Before then we start also tomorrow with multi-grid, meaning fast solvers. Now remember, tomorrow we are not here, we are in the room F4. Any questions? Then we stop here.